In today's lesson, we're going to discuss molecular polarity. Before we begin talking about molecular polarity, though, let's revisit bond polarity because we have to have a good understanding of bond polarity and what a dipole is before we can truly understand what molecular polarity involves. So let's just take a look first at a molecule like HBr, hydrogen bromide, or hydrobromic acid if it were in water. And so if we had hydrogen bromide and we wanted to determine if this had a dipole, of course, we would then need to look at the electronegativity differences between hydrogen and bromine. And hydrogen happens to be 2.1, has an electronegativity of 2.1. Bromine has an electronegativity of 2.8. So we look at the difference between these two. So our electronegativity difference, absolute value of the two. And so we get here 0.7. And as we had discussed in the previous lesson, a difference of 0.5 or greater would be a polar bond. So hydrogen bromide then would have a polar bond, whereby the dipole would be heading towards the bromine because it has the higher electronegativity. So we would draw in our dipole as such. Okay. Now, little side note, when I draw that in, the bromine having a higher electronegativity would be negative, and the hydrogen having the lower electronegativity then would end up being positive, keeping in mind the two are still bonded together. They're still sharing electrons, just that the electrons are being diverted, so to speak, towards the bromine. And so then we can draw our arrow right through that plus and that negative. Okay, so that shows our dipole. So this is a real simple molecule. We can see then that the electrons are being pulled to one side, and this whole molecule then would be considered to be polar. But again, this is a simple molecule. If molecules get a little bit more involved, a little more complex, sometimes even if you have dipoles, there could potentially be a dipole, the dipoles might cancel each other out. So the molecule itself could end up becoming nonpolar. Let's take an example. Looking at carbon dioxide. If we were to consider carbon dioxide, and I look up, well, if I do the Lewis structure for it first, and this is the first thing we have to do. We have to do actually the Lewis structure and the 3D diagram for it. So I do the Lewis structure, which will end up looking like this. And we can see that because it has two double bonds like this, they'll repel each other, and the molecule will be linear in its shape. So we know this is going to be linear, whereby the oxygens are on the opposite sides of our carbon atom. Now, if I look up the electronegativities, carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. And so electronegativity difference in this particular case is then going to be equal to 1.0. And again, greater than 0.5, greater than or equal to 0.5, would give us a polar bond. So in this case then, we would have a dipole that would go from the carbon towards the oxygen. But then we'd also have a dipole going from the carbon towards the other oxygen. So because there are dipoles going in opposite directions as defined by the electronegativity difference, these two dipoles would cancel each other out, analogous to a tug of war going on between two teams that are equally strong. The rope doesn't go anywhere. So these two are going to cancel each other out, and as a consequence, this molecule then will be nonpolar. So here we have a situation where the bonds would be polar by themselves. Okay, the bonds would be polar by themselves if they were not part of the entire molecule. But because the bonds are opposite in their direction, they will cancel each other out, and the molecule then is called nonpolar. So here we have a situation where it's a nonpolar molecule with polar bonds. And this can happen in other shapes as well. So for example, if I had, let's just take into consideration SO3, sulfur trioxide. Now if I had sulfur trioxide, if we do the Lewis structure for this, it would end up looking like the following. You'd have one double bond to an oxygen and single bonds to the other two oxygens. So our shape, our molecular shape for this would be trigonal planar. Now, if I were to consider the electronegativities of sulfur and oxygen here, sulfur has an electronegativity of 2.5 and oxygen has an electronegativity of 3.5. So again, we have a difference here of 1.0. And just like the carbon dioxide with electronegativity 1.0, this is going to be a polar bond. So in this particular case, again, the bond's going to be polar. So the dipole, if it were to be drawn in, would go from the sulfur towards the oxygen in all three of these bonds. And the fact that this one's a double bond has no bearing on the dipole. Okay, so it doesn't really matter. So we'd have these three dipoles, and because of the symmetry of the molecule and the symmetry of the opposing directions of the dipoles, this whole molecule too will be nonpolar. So they will cancel each other out. So here's another case where the molecule then is nonpolar. Let me try that again. Nonpolar. Now, again, these aren't the only two, of course. We have a symmetrical situation when we have tetrahedral, and an example of that would be like carbon tetrachloride. So I have carbon tetrachloride. The molecule will look like this. We have carbon, and then we'd have a single bond to our chlorine, another single bond to our another chlorine, and then one of them, because it's a three-dimensional molecule, one of the chlorines is going to be below the plane, and the other chlorine will be above the plane. And so we'd have a dipole now going in all four directions as such, because the electronegativity difference here is carbon is 2.5, chlorine is 3.0, all right, and the electronegativity difference here is going to be equal to 0.5. Now, when we're considering 0.5, if it's 0.5 or 1.7, 1.7 and 0.5 are going to be inclusive for a polar bond. Okay, so I guess stated another way, 0.4 or less would be nonpolar. So here I'm going to have then, we have our dipoles drawn in. And although it's kind of hard to visualize something like this because it's three-dimensional, all right, this molecule then would be nonpolar because each of these dipoles would be countering each other. So again, situation where the bonds here are going to be polar and our molecule nonpolar. Now, what if you have asymmetrical distribution of your polar bonds or your dipoles? So, for example, again, going back to carbon dioxide, if we were to take one oxygen away and just consider carbon monoxide, we'd have a triple bond between the two, and carbon having the lower electronegativity would be positive and the oxygen would be negative. So here again we have a simple molecule, but there's nothing countering this dipole. So therefore this molecule will be polar because the bond is polar and there's nothing to counter it. Also consider SO2. If we were to look at SO2 or sulfur dioxide, in sulfur dioxide, if we were to do the 3D diagram for this one, we'd have sulfur double bonded to one of the oxygens, and then there would be a single bond to the other oxygen and an unshared pair here. Now, as we showed before with SO3 or sulfur trioxide, we had a dipole going from the sulfur to the oxygen. So we're going to have a dipole going from the sulfur to the oxygen here and to here. But in this case, unlike carbon dioxide, the dipoles will not are not directly opposing each other. And so this molecule will be polar. So going back to carbon monoxide, these dipoles are directly opposing each other. Okay, they're directly opposing each other. So therefore, those dipoles will cancel each other out, and you will have a nonpolar molecule. But in this situation, these dipoles are not directly opposing each other, and we have an unbalanced distribution of these electrons. So therefore, here we have a situation where we have the bonds are going to be polar, but the molecule will also be polar because of the asymmetry. We can also consider something like nitrogen trifluoride. Now, nitrogen trifluoride, the molecule looks something like this. If we were to do the 3D diagram, we could put two of those fluorides in the same plane with the nitrogen. And then the third fluoride would either go above or below the plane that is there. This is supposed to be a dashed line, apologize. And let's assume that the other fluoride is below the plane. And then we'd have an unshared pair here. Now, whenever we have an unshared pair, it throws off the symmetry a little bit. And we have to first determine now, again, if this is going to be, if the bonds themselves are polar. So we look at nitrogen and we look at fluorine individually. Nitrogen has an electronegativity of 3.0, and fluorine is 4.0. So the difference here is going to be 1.0. So now we know again that we have a polar bond here. So the nitrogen to fluorine bond will be polar, and we'll have a dipole going to each of these. And now again, because of the asymmetry, in other words, we have this unshared pair that kind of throws things off a little bit, these dipoles will not cancel each other out. And we have to be careful, even looking at this dipole here and this dipole here, these are not directly opposing each other because this fluorine atom right here is below the plane, so it angles down below the paper here. So again, here's a situation where we'd have polar bonds, and the molecule is going to be polar because of the fact of the asymmetry. Determine if a molecule is going to be. So when we try to determine if a molecule is going to be polar or nonpolar, we must first consider the Lewis structure. We have to construct that. And then once we've constructed the Lewis structure, then we take a look at and determine the molecular shape. Because we need to understand the molecular shape and look at its symmetry to determine if this molecule is going to be polar or nonpolar if it has polar bonds. So then the next thing we need to look at then is the bond type, if it's polar or nonpolar. So here we look at the bond type. And we ask ourselves, is it polar or not? Okay, so if the bond type happens to be polar, then we need to look at the atom and see if it has any unshared pairs. And so let's just put in here central atom, and I'll just put unshared pairs, question mark. Because if it has unshared pairs, then it's going to throw off its symmetry. So if the central atom has unshared pairs, then the molecule is going to be polar. If, however, the molecule or the central atom does not have any unshared pairs that are available, in other words, all the central atom electrons are being occupied, then our molecule will, I'm going to say, most likely be nonpolar. I'm going to show you some examples where that won't be the case because it will have symmetry. So we'll put no here. So there we have it for if the bonds are polar. But what if the bond is nonpolar? Okay, what if there is no polar bond in the molecule? Well, if there are no polar bonds in the molecule, then automatically the molecule has to be nonpolar. So, once again, first we consider the Lewis structure. Once we've created the Lewis structure, we look at the molecular shape. Once we look at the molecular shape, then we can draw in our dipoles for that matter, and we consider if the molecule is going to be polar or if the bonds are polar or nonpolar. If the bond is polar, well, then we have to look at the central atom if it has any unshared pairs. If it has unshared pairs, well, then it's going to throw off the symmetry, in which case you'll have a polar molecule. If the central pairs are all occupied, then you'll have a nonpolar molecule. And again, if the bonds are nonpolar, well, then automatically the molecule has to be nonpolar. Now, let's just consider, though, one or two examples that are exceptions to this rule because they are important. When determining the molecular polarity, what we really are considering is the symmetry of the polar bonds. So we have to be careful with the diagram that I just created for you because there are exceptions to that rule. And for example, if I had carbon bonded to bromine and to fluorine, okay, so we do the Lewis diagram for it, and it might look something like this. So we do the Lewis structure, and it ends up looking like this. We're going to have bromine attached to the molecule on two of the sides and fluorine in the other two. And it looks like something like this. And of course, then we'd have all 8 dots around each one of the bromines and the fluorines. So the 3D diagram for this, we'd have carbon in the middle, bromine, fluorine, and bromine. So it's a 3-dimensional diagram whereby here I have this bromine and this fluorine in the same plane. The fluorine is below the plane, and this bromine here is above the plane. So I got to keep in mind that, again, this is a 3-dimensional object. So that's our next step. We've done now the Lewis structure and 3D diagram. The next part is we have to consider then the bond polarity. So we look at carbon and bromine bromine here. And carbon has electronegativity of 2.5. Bromine is 2.8. So the difference here is going to be 0.3. So a difference of 0.3 would be nonpolar. Because 0.4 or less will be nonpolar. So there will be no dipole that will exist between our carbon and our bromine here, and there's going to be no dipole between this carbon and that bromine there. So then we take a look at the carbon and the fluorine. Now carbon is again 2.5 and fluorine 4.0. So our difference here is 1.5. So this is going to be strongly polar. Okay, so this definitely be polar. So therefore, we're going to have a dipole that will exist between the fluorine and the carbon. So our dipole will come out of the carbon towards the fluorine, like so. So in considering this situation, we can see that these dipoles will not cancel each other out because they're not directly opposing each other. So this would be a case where all the central atoms' electron pairs are being occupied here. Okay, so all the central electrons are being occupied, so there are no unshared pairs. However, because these dipoles here exist here, but not with the bromine, carbon and the bromine, then this molecule will be polar. In other words, these two dipoles can't cancel each other out because they're not directly opposing each other. Now you might think to yourself, well, what if I drew it like this? And then you'd have your dipole here and your dipole here. And you might say, well, now, if I draw it like this, then those two dipoles are directly opposing each other, therefore they'll cancel each other out. Well, that isn't true because you got to keep in mind that this bond right here is actually falling below the plane of the paper. So in reality, there's going to still be a 109.5 degree angle between those two bonds. It's not going to be 180 degrees as it appears almost on the paper here. So you got to keep that in mind when you're working with these three-dimensional objects. So here's a case where you have an exception to the rule where all the pairs of electrons are occupied, but the dipoles are not symmetrically opposing each other. Therefore, this molecule will be polar. And that is polar molecules.